Hello, it's Keith here, and this is lesson 19 of the Suck Hunt series of my Z80 programming tutorials, and today we're going to be looking at Suck Hunt on the MSX2. Suck Hunt doesn't support the MSX1, but it does support the MSX2 because the MSX2 has rather nice 16 colours which can do things like that, so that's what we're going to be doing. Now, if you're not familiar with Suck Hunt is of course stereoscopic. It uses anaglyph glasses, which means we have to combine two images together to make the 3D effect. If I just slip the game over here and I change the control mode to mouse and start the game here, you'll see the gameplay in action. Now, the game itself, we are controlling a gun here, and we have to shoot the bats as they come onto the screen, and the bats are of course vampire bats, which is why the game's called Suck Hunt. And basically we have these 3D graphics, and the sprites will come closer to us as the bats move forward towards the player, and when they get to the front of the screen in 3D, that is, we die. So we need to draw these 3D graphics, and the way this is done is with an XOR effect. Let's just go quickly over to the blackboard and let's discuss it. So if we've got our screen here, we basically draw two sprites, a red sprite like that, that's a sprite, and we draw a blue sprite. That's a sprite as well. They should be the same size, but my artistic skills are letting me down. And the combination of those two will make the 3D effect that you can see above me. Now, this is a problem on this system because on the other systems we've been using XOR graphics and bitmap images to do this. Now we can sort of do the same thing here, but in the past what we've done is we've real-time converted the 4-color graphics into the correct bit positions and then XOR'd them in onto the screen, and that's created the effect. Now, to my knowledge, there's no way of doing that on the MSX2. So what we've done is we've taken those graphics when the game loads up. The graphics are 4 colors in ROM, and we've converted them to 16 colors, and we've stored 2 different versions of each sprite for those 3D versions, the red version and the blue version, and then we can mix those together with our XOR effect on the screen and get that you can see up there. Now, if we go over to this window here, you can see this is the graphics here. This is a screenshot of the VDP memory, the hidden area using the debugger, and this is how the graphics are stored in the game VRAM. So these were converted from 4 colors as the game started up, and you can see here at the start we've just got the font twice. The font is also 3D, you see, so we need that. But then what we've done is we've converted each of these sprites first as a red sprite and then as a blue sprite, and each time we're moving along by the width of the sprite, and when we get to the end of the line we have to jump down. Now this does leave some areas like this here and this here that are unused, but it was convenient to just make this a simpler thing, and I wanted to do it in real time. I wanted all of the dirty work to be done by the software itself rather than having to pre-do it in Sprite editor or something, which, while that would be faster on the game starting up and might save some VRAM, it would mean that I was having to do a lot more manual work every time, and I didn't want that precedent setting for this game. I wanted this game to be, working with the same data in all cases where possible. So that's what we have to do. So we have to create that image in VRAM off screen. This will occur at memory address at Y line 256 onwards, which is invisible. That's outside the visible area. The game doesn't use 2 image screen buffers. It just uses 1. The XOR effect and the fact that the screen doesn't update that much means that we only need 1, and that's part of the tricks and how this game works. Okay, let's go over to the source code and let's have a look at what we've got. The way we upload the graphics to the VRAM does differ a little bit depending on the kind of graphics. Now, the main sprites here are done in this section here, and what we do is we use this function upload one sprite. This will read in the settings of the sprite from a lookup table which all of the versions of this game have. There's a constant lookup table with the sprite offsets and the X and Y sizes. The MSX itself has a special extra lookup table which is the equivalent locations in VRAM of those sprites, and that's used during the drawing routines. However, that table doesn't exist for the fonts. The fonts are effectively lots and lots of tiny 8x8 sprites, but it would have been a massive waste of memory to have such a huge table when they were so easily calculatable just by the character number you wanted to show. So that's why we're using upload sprite alt for that sprite, but for the main sprites we repeatedly use upload one sprite. The final kind of graphic is the pre-colored 16 color graphics. The title screen, I stopped the game because the music was over loud even with the volume turned down. The title screen is actually 16 colors, and that's true 16 colors. That's not been converted to 4, and the reason for that is the 3D effect is not being calculated in real time. It's been pre-done into the image. That gave a better 3D effect and a nicer title screen, so that's why that's done. But that means we're actually transferring this data to VRAM directly, byte by byte, from the data in the font. That's the title screen there. That's a I call it pre-compiled 16 color 3D, because the 3D effect is not being calculated in real time, and that means we can only turn it on or off, and we turn it off by basically hiding 16 of the colors, hiding one of the eyes effectively. So how do we actually get those sprites into RAM? Well, here's the routine, and what we've got here is we've got sprite info, which is the source data. This is the lookup table of all of the sprite information, and you can see it just here. Here's sprite info, and we've got a calculated memory address of the sprite. These are all in ROM as full color sprites, and then we've got the width and height of the sprites. So this really doesn't change for the different versions of this game. So this is the source data, and then the other thing we have is the MSX destinations. Now these are referred to as sprite MSX data, and you can see that just here. So this is just at a memory address, which we assume will start as 0, because we will populate it with the data as this routine runs. And I can hear that music again, it's very loud. So basically what we're doing here is we are first calculating the address in sprite info. There are 4 bytes for each sprite in that table, so we're multiplying our sprite number by 4 effectively, and we're calculating that offset. Now the sprite info in the MSX table, each image in that table uses 6 bytes, but there were 2 images per sprite. If you remember, there is a left eye image and a right eye image, so each of those, that red Chibico will have 6 bytes, and that blue Chibico, that cyan Chibico, will have 6 bytes. So we're effectively doing another shift, and then we're adding again. So we're adding the sprite number times 8 plus the sprite number times 4, effectively giving us 12, because there's 6 bytes per eye definition. Then what we're doing here is we're defining a mask, and that's for the left eye mask and then the right eye mask, and we're uploading this first sprite using this conversion routine, adding 6 to our destination and uploading the second one, and that's so we've got those 2 versions of the sprite in memory. The routine for uploading those sprites is here. It's a little bit long, but here it is. So we are getting the sprite width here. That is in pixels. So we need to convert that to bytes. There's 4 pixels per byte, so we're shifting that to the right twice there. We are then getting here the height, and then we're doing a very crude multiplication of the height to get the number of bytes that this image will require. What we're then doing here is we're getting the source bitmap data from it, which is the 4-color bitmap data here, and we're then converting the first byte. We're going to be using the command HMMC here, which will transfer an image from byte data from our CPU to the VDP, but rather annoyingly that command insists on having the first byte passed to it. So we're converting the first byte here, and then we convert the rest quite a lot later. So what we're doing next is we're calculating the position that this sprite is going to appear. So what we're doing here is we're getting the height of the current sprite, and we're adding this to the Y position that we're drawing our sprites. What we're going to do next is we're checking to see if the height of this sprite added to the current line of the sprites is higher than any of the others. Because when we're doing a sprite like this is a very tall sprite, this Chibico here, but then this sprite later on is very short. However, when we get to the end of the line, we need to jump down to the first line that's below both. So we're jumping down to the taller sprite, which is that Chibico. And so that's why we're doing this here. We're calculating the highest sprite. We're then getting the width of the sprite, and we're adding that to the current position in VRAM. And if we've gone over the current width, i.e. 256 pixels, we've got to the edge of the screen. Like here, you can see that tiny bat there was the last sprite that would fit, and then there was another little bit of space, but it wasn't enough for this big bat here. So we have to, in that case, do what I've referred to here as a retry. That's where the sprite doesn't fit and we need to recalculate and start again. And that's what we're doing here. We're taking our maximum Y line, adding that, setting that to our current Y line, and then we're resetting the X position. We're basically doing a carriage return, jumping back to the far left. And so again, in the case of here, the next sprite wouldn't fit. So we jump back to the far left here and we start again and start drawing sprites at the far left. And that's what we've done there. And in that case, we have to jump all the way back up to here and start calculating our sprite position once again. It's a bit of a pain, I know, but that's what we have to do. Now, along the way, we're writing all of the position data and width and height of the sprite that we are going to transfer to memory to IX with these offsets. And that's the data for the sprite when we want to show this sprite back onto the screen. We're going to need to know the X and Y position in VRAM and the width and height of the sprite. And so that's why we're storing those. We're then transferring the actual sprite data into VRAM, and that's getting us ready for the actual data to be in RAM so we can use it. Now, once the initialization is ready, we then need to skip over and we need to send the second byte to VRAM here. Now, basically, we have two different versions of these byte drawing routines, and this is because, as I say, the source data is 4 color, but the destination data is 16 color. So do byte 1 is getting the 2 pixels in the leftmost nibble, the top nibble of the byte source data. The second version is getting the bottom nibble and the 2 pixels contained within, and it's converting them to 16 color, and then it's using the mask that we specified before sending that data to VRAM, and that's what's building up the table here. It's rather a pain, I know, but that is the problem. Now, of course, there would be easier ways of doing this from a software point of view on the MSX. If this game was only written for the MSX, we would have done things very differently. But for me, I wanted to port this game with as little changes to the multi-platform code as possible. So the rule I sort of set up was that the multi-platform code can't really change. The system has to adapt to the multi-platform code, or the game isn't being ported to that system. So that's literally what we're doing. We're writing an interpreter to port the graphics and a bridge that with that MSX lookup table for when we're looking to draw the sprites to the screen. Now, the irony of all this is the actual sprite drawing to the screen routines are pretty easy compared to some of the other systems, because we've got those VDP commands to transfer the data for us. We're using a logical transfer so that we can have that XOR effect. But basically, all we need to do is we need to get the sprite data source for our lookup table that we're using. We then get the sprite number here. And what we're going to do is we're going to calculate the offset of the sprite data. We then get the Y source, the X source, the width and the height of the sprite. And this is the data that we're going to need to draw the sprite from the VRAM to the screen. And so that's what we've done there. And all we do is we use the LMM via stack routine here that I wrote before. This will transfer all of the variables that we've put into our various registers here, and it will send those to the VDP via a sequence of out-I commands. Now, to draw the 3D sprite, there's 2 versions. First, we use the show sprite L routine, which would show the red version of the sprite. Then we use the show sprite R routine if we're currently in 3D mode. You see there's a return Z if we're not in 3D mode. That was done in self-modifying code on the other systems, but this system we're running from ROM, so we couldn't do that. Drawing that second sprite is extremely easy though. All we do is we change the offset of our source data, our source lookup table entry. We add 6, and that effectively jumps us from the left eye to the right eye, and that's how we draw that second image. So that actually is pretty straightforward, which is a relief. Now, the other thing that we do probably want to just discuss is the tile maps. Now, there are a few tile maps in the game. The introduction sequence, which you'll see starting up soon, that uses a tile map. The tiles are 8 by 4, 4 lines tall in that case. So it was a memory saving thing, but you can't tell because they only appear quickly. And the main game title screen image is 8 by 8, and the game over also uses tile maps as well. Now, the tile maps themselves, those are almost 1 byte per tile number. Any number under 255 is a single byte, so 0 is tile 0, 100 is tile 100. But when we have a value of 255, if I can just find one, here's one. So 255, 12, that is tile number 255 plus 12. And that was just to make the tile definitions a little bit shorter, but allow for up to 512 tiles, which the Sega Master System version did use. When it comes to drawing the tiles and also drawing the fonts, we've got some alternate versions of our sprite routines here. So here's our show tile map routine here. This is to show the full screen image here, the second image you could see if I turn that magnifier off there. So that's what we're doing here. All we're doing basically is we're loading in our tile number, seeing if it's less than 255. If it's less than 255, we are just going to show with the print tile routine. If it's over 255, what we're actually doing is we're adding 64 to the starting Y line of the tile number. Now, just like with our font, basically there's 32 tiles on each line, and so the first 255 tiles will use 64 pixel lines of memory, and so we're just skipping down there to the second bank of tiles and then running our print tile routine. The print tile routine, pretty straightforward here. We're using the cursor X and the cursor Y, which are our font routine, used by the font routine as well. We're calculating our tile position based on the tile number here, taking the top 3 bits of the tile number here. This is effectively the Y line, if we multiply that by 8. And we take the bottom 5 bits here. These are effectively the X line offset if we multiply by 8. And this gives us our memory position for the tile. If we add that to our offset of course being the start of the bitmap data for the tiles, we're then using the LMMM command here again to transfer that 8x8 tile to the screen. Our font routine is basically the same. Here's our print tile routine. This time we're using the font at the top, but basically again we're having to do the same kind of calculations, but the fonts are actually drawn in with the 3D effect. So what I do in this case is I'm patching all of the settings that I calculate for the X and Y source of the characters within this font, and then I'm setting up some data in the correct format for the sprite drawing routines so that I can use the draw sprite from IY function to draw that character to the screen. And again, that was needed because the other systems are doing that. If I hadn't done it in that way, and if I hadn't done a lot of these things in this way, I might have saved some MSX coding, and it might have been a little bit faster, but the multi-platform code that worked fine on all the bitmap systems would not have worked on this system. So that is why I've done things in an overcomplicated way potentially here. It was to save the code, the multi-platform coding. And one thing that I have learned, and not necessarily regret, but one of the unfortunate things about this system is it took a long time to port the game to a new system. When I'd done a game in the past like YQuest, it was taking me a day or a few hours in the evening to port the game to a new system. The second game was taking a minimum of 2 weeks to port to a new system, and I think this version took 3 weeks, which means it isn't really possible for me to port this game to any more systems because I'm only making 3 tutorials out of this code, and that's 1 week's videos, so I've got a deficit of 2 weeks basically. So unfortunately my future games I'm going to have to design in a more platform efficient way, meaning more of the code is multi-platform and less is platform specific, just so that I can viably make games and put them on my YouTube channel. So again, as I say, I understand the code isn't the most efficient from a MSX point of view, but it's the most efficient from my workload and producing results that are, shall we say, economically viable from the point of view of the rewards versus the time it took to make them. So I think that's something to bear in mind if you're writing games. I know a lot of you won't be writing multi-platform games, but you will have other time constraints in your life that you need to work around, and often the best game and the most slick and impressive game takes an awful lot of time, and sometimes you just need to work out what you can realistically complete within the time constraints you have, and that is often it's better to make a game that's finished than to not make a game, I guess is what I'm saying. Anyway, as I was saying, if you liked what you saw and you want to support my content making more games, you can buy my book, Learn Multi-Platform Assembly with Chibi Akamas. Covers Z86, 502, 68086 and ARM, as you probably know, as I always mention it, and it's available on Amazon, as you probably know. You can download the source code and the built game for Suck Hunt on the MSX from my website, and you can use the source code in any way you want. If you find use for some of it in your own commercial games, go ahead, have some fun with it. That's what it's there for. Hope you've enjoyed this. Thanks for watching today, and goodbye.